Imagine standing on the tarmac, watching a jet engine roar to life, flames blazing inside at temperatures hotter than the surface of a volcano, spinning thousands of times per minute. Yet somehow nothing melts. How is this even possible? What secret allows these metal giants to survive such unimaginable heat while propelling massive aircraft across the skies at incredible speeds? Today we're diving into a world where physics, engineering, and materials science collide in ways that defy intuition. From the microscopic structure of superalloys to the invisible rivers of air-cooling turbine blades, every detail has been designed to conquer the extreme. By the end of this journey, you'll not only understand why jet engines don't melt, but you'll see the genius of human innovation and the astonishing power of science working in perfect harmony. Buckle up, because what you're about to discover will completely change the way you look at the machines that fly above us every day, and it's going to be absolutely mind-blowing. Jet engines are some of the most extreme machines ever built, and one of the most astonishing facts about them is the sheer intensity of the temperatures they endure. Inside the combustion chamber, air is compressed to incredibly high pressures and then mixed with fuel, which ignites to produce flames reaching temperatures of over 2,000 degrees Celsius, hotter than the surface of some volcanoes and well above the melting point of common metals like aluminum or steel. At first glance, it seems impossible that anything made of metal could survive in such a hostile environment. The metal components, particularly the turbine blades and combustion chamber walls, are subjected not only to heat but also to enormous mechanical stresses caused by rotation at thousands of revolutions per minute. Despite this, these parts maintain their shape, strength, and function, allowing the engine to operate reliably for hundreds of hours under extreme conditions. The secret lies in a combination of materials, science, and engineering design, which ensures that even at these blistering temperatures, the metal does not reach its melting point. The high-speed airflow through the engine carries heat away, and precise temperature control is maintained throughout the operation. The fact that engineers can make machines withstand conditions that would instantly destroy ordinary metals is a testament to human ingenuity and our understanding of thermodynamics and material behavior. The extreme temperatures inside a jet engine highlight the remarkable challenge of balancing heat, pressure, and mechanical forces, creating a scenario where physics seems almost defied, yet it all works perfectly due to careful design and advanced materials technology. The ability of jet engines to survive extreme heat is largely due to the use of advanced materials specifically engineered for high-temperature performance. These materials, often called superalloys, are far stronger and more heat-resistant than ordinary metals. Most superalloys are based on nickel or cobalt, sometimes with titanium, and include small amounts of elements like aluminum, chromium, and molybdenum. Each of these additions serves a precise purpose. Aluminum helps form a protective oxide layer that resists corrosion, chromium strengthens the alloy and prevents oxidation, and molybdenum enhances high-temperature strength. The structure of these alloys is carefully engineered at the microscopic level to resist deformation under stress, even when exposed to temperatures exceeding 2,000 degrees Celsius. In addition to bulk material strength, modern jet engine components often have special coatings that act as thermal barriers, reflecting heat and further protecting the underlying metal. Some turbine blades, for instance, have ceramic coatings that can withstand the searing combustion gases while allowing the metal beneath to remain cool enough to maintain structural integrity. The combination of these advanced metals and coatings allows jet engines to operate at temperatures that would instantly melt conventional steel or aluminum, pushing the limits of what materials can endure. Engineers also continually experiment with new alloys and hybrid materials to improve performance, reduce weight, and increase efficiency, ensuring that every component can survive in one of the harshest environments imaginable, while maintaining reliability and safety. One of the most fascinating reasons jet engines don't melt is the advanced cooling technologies built directly into their design. Even the strongest metals have limits, and the temperatures inside a combustion chamber can far exceed what the superalloys alone can handle. To manage this, engineers use a technique called internal air cooling, where cooler air from earlier stages of the engine is channeled through tiny, precisely engineered passages inside turbine blades. This air flows like a river inside the metal, absorbing heat and keeping the blades below their melting point. The design of these passages is incredibly complex, often resembling microscopic mazes that maximize cooling efficiency while maintaining the structural integrity of the blade. In addition to internal cooling, many turbine blades are coated with thermal barrier coatings, usually made of ceramic materials, which can reflect and insulate against the extreme heat of the combustion gases. Some blades even have perforated surfaces that allow a thin layer of cooler air to flow along the outside, creating an insulating boundary between the hot gases and the metal itself. These cooling strategies work together to ensure that, despite facing temperatures hotter than molten lava, the engine components remain intact and functional. This combination of clever design, precise airflow management, and protective coatings allows engineers to push engines to higher efficiencies and higher operating temperatures than would otherwise be possible, demonstrating an incredible synergy of physics, materials science, and aerodynamics in one of the most extreme environments humans have ever engineered for. Another crucial factor in why jet engines don't melt is the role of aerodynamics and efficiency in managing extreme heat. Jet engines are not just machines that burn fuel. They are precisely engineered systems where airflow is carefully controlled to maximize energy extraction while minimizing damage to components. The shape of turbine blades, nozzles, and combustion chambers is designed to ensure that hot gases flow smoothly at incredible speeds, preventing heat from lingering in one spot long enough to cause melting. High-speed airflow acts like a conveyor belt, constantly moving heat away from critical surfaces and distributing it evenly across the engine. Engineers also design engines to operate at optimal pressure and temperature ratios, which allows the gases to expand efficiently and transfer energy to the turbine blades without overheating them. Even small imperfections in airflow can create hotspots that risk structural failure, so every surface is sculpted to guide air and fuel mixture precisely. The combination of smooth gas flow, careful expansion, and efficient energy conversion reduces the thermal stress on the metal parts. This aerodynamic efficiency works hand in hand with advanced materials and cooling systems, creating a balance where the engine can operate at extreme temperatures yet remain safe and reliable. Essentially, the physics of fluid flow and thermodynamics are harnessed not just for propulsion, but as a protective mechanism, showing how controlling the motion of gases is as important as the strength of the metals themselves. The resilience of jet engines at extreme temperatures is also deeply rooted in thermodynamic principles that govern their operation. Jet engines operate on the Brayton cycle, a sequence of compression, combustion, and expansion that converts heat energy into mechanical work with remarkable efficiency. Air entering the engine is first compressed to high pressures, which raises its temperature even before fuel is ignited. When fuel burns in this compressed air, it produces gases that are extremely hot, yet these gases expand rapidly as they pass through the turbine blades. This rapid expansion is key. As the gases expand, they lose heat energy while transferring it to the turbine, converting thermal energy into rotational motion. The faster the gases expand, the less time they have to overheat the metal components, effectively using the physics of expansion to protect the engine from melting. Additionally, the cyclical nature of the Brayton cycle ensures that the energy release is controlled and distributed, preventing sudden spikes in temperature that could damage the blades. Engineers also carefully match the turbine design to the expected pressure and temperature profiles, so the metals experience loads within their tolerances. This interplay of compression, combustion, and expansion allows the engine to operate at temperatures that exceed the melting point of ordinary metals, while keeping the actual components within safe limits. By applying the laws of thermodynamics in precise and innovative ways, the engine harnesses the immense energy of hot gases without succumbing to it, demonstrating how fundamental physics can be engineered to achieve both power and survival in extreme conditions. The ongoing ability of jet engines to withstand extreme temperatures is fueled by continuous innovation in engineering, materials, science, and manufacturing techniques. Modern engines push the limits of what metals and alloys can endure, and achieving higher efficiency requires ever hotter operating conditions. One of the most transformative advances is additive manufacturing, or 3D printing, which allows engineers to create intricate internal cooling channels and complex geometries that were impossible with traditional methods. These designs enable air to flow precisely through turbine blades, cooling them from the inside while maintaining structural strength. Engineers are also developing new superalloys and hybrid materials that combine metals with ceramic or composite elements, providing extraordinary heat resistance and reduced weight. Coatings continue to evolve as well, with thermal barrier coatings becoming thinner, stronger, and more durable, reflecting heat away from critical components. Computational modeling and simulation play a huge role in this innovation, allowing engineers to predict how metals will behave under extreme conditions, optimize airflow, and design engines that extract maximum energy without exceeding material limits. Every iteration of engine design incorporates lessons from previous failures, field data, and breakthroughs in material science, creating components that are lighter, stronger, and able to operate hotter than ever before. This relentless pursuit of improvement means jet engines not only survive extreme heat, but thrive in it, combining physics, materials, science, and engineering ingenuity to push the boundaries of human achievement and enabling aircraft to fly faster, farther, and more efficiently than ever imagined. If you want, I can now turn all 6 keynotes into a full, engaging speech in a high-energy, mind-blowing physics style suitable for video narration. Do you want me to do that next? In conclusion, the reason jet engines don't melt is not a single secret, but a remarkable combination of advanced materials, ingenious cooling systems, precise aerodynamics, thermodynamic mastery, and relentless innovation. Every component, from turbine blades to combustion chambers, is carefully engineered to withstand temperatures that would destroy ordinary metals, turning extreme heat from a threat into a source of power. This incredible synergy of physics, engineering, and materials science allows engines to propel aircraft at incredible speeds, while surviving some of the harshest conditions humans have ever created. It's a testament to human curiosity, creativity, and the relentless drive to push boundaries beyond what seems possible. Good luck to everyone exploring the wonders of science and engineering. May your curiosity fuel your discoveries, and may you continue to unlock the secrets of the universe. Thank you for joining this journey into the mind-blowing world of jet engines and the extraordinary technologies that make flight possible. Keep questioning, keep learning, and never stop being amazed.